You know, it's pretty mind-bending when you think about it. Over a century ago, Albert Einstein came up with this wild idea that the most violent events in the universe would send out ripples, not through space, but in space and time itself. Today, we're going to dive into the physics behind these cosmic ripples, gravitational waves.
Okay, but that brings up a pretty massive question, right? If the very fabric of reality is shaking, how in the world are you supposed to see that? I mean, how do you even begin to look for something that's totally invisible and is literally everywhere at once?
Well, the trick is to stop thinking about seeing them at all. For pretty much all of human history, astronomy has been about light. Telescopes, radio dishes, you name it. It's all about what we can see. But this is different. As the source material puts it, it's a whole new window on the universe. It's like we grew a brand new sense. It's not about seeing, it's about listening to the cosmos.
All right, so let's get down to it. What are these things? Well, a gravitational wave is basically a ripple in space-time. The classic analogy is perfect. Picture a trampoline. If you drop a bowling ball on it, the surface warps, right? Now imagine throwing two bowling balls on there and getting them to spin around each other like crazy. That's what's creating these waves, these ripples that spread out across the universe.
And here's the wild part. This isn't some rare, exotic thing. It's happening all the time. The universe is basically humming with these gravitational waves. You've got the leftover whispers from the Big Bang, you've got stars collapsing, you've got neutron stars doing this insane orbital dance. It's a constant cosmic symphony out there.
Okay, so the idea is cool, but trying to actually do the math on this stuff, hoo boy, that's a whole other level of difficult. Einstein gave us the playbook for sure, but his equations are, well, they're a beast. So how did physicists even begin to get a handle on them?
So, this is the starting point, the whole enchilada, Einstein's full field equation. And it's gorgeous, right? It perfectly describes how matter and energy tells space-time how to curve. The problem? Actually solving it for a real-world scenario, like two black holes spiraling into each other, it's next to impossible. Just way, way too complex.
So, what do you do when the math is too hard? You find a clever shortcut. And that's exactly what physicists did. They realized, hey, instead of trying to model the absolute chaos right at the source, why don't we look at the waves way, way out here, where they've spread out and are a lot weaker? This approach, this approximation, is called linearized gravity, and it was a total game changer.
And this is why that idea was so brilliant. Take a look. That monster of an equation from before, it simplifies down to this. And if you've ever taken a physics class, this should look super familiar. It's a classic wave equation. The same basic math that describes light waves, sound waves, you name it. All of a sudden, the impossible problem becomes, well, manageable.
All right, so we've wrestled the theory into submission. Now for the fun part. What does it actually take to make one of these waves? What's the cosmic recipe?
You know, the easiest way to wrap your head around this is to think about something we use every day, electromagnetism. How does a radio antenna work? It just wiggles electrons back and forth, and that creates radio waves. Simple enough. Well, gravity works in a similar way. You wiggle a massive object and you get gravitational waves. But, and this is a big but, if you look at that last row in the chart, you'll see there's a really important catch.
And the catch is something called the quadrupole moment. Now, don't let the name scare you. Here's the deal. For radio waves, all you need is a changing dipole. Think of a plus and a minus charge moving apart and together. Super simple. Gravity's pickier. A perfectly spherical star that just pulses in and out? No waves. You need an asymmetry. You need a change in the shape of the thing. The perfect mental image is a dumbbell spinning end over end. That's the kind of motion that churns out gravitational waves.
And this formula right here, this is basically the recipe card. Again, don't worry about solving it, just look at what it's telling us. The P on the left is the power of the wave, and it's tied to how fast that quadrupole moment, that shape, is changing. So the takeaway is simple. The bigger your masses are and the more violently you can whip them around and change their shape, the more powerful your gravitational waves are going to be.
Okay, so we've got our recipe now. We need something massive, and we need its shape to be changing really, really fast, and ideally in a way we can predict. So, where in the whole universe are we going to find a perfect setup like that?
Well, let me introduce you to the binary star system. This is it. This is the jackpot. You've got two huge objects, maybe even super dense neutron stars, locked in this incredible dance. As they spin around each other, their shape, that quadrupole moment, is changing constantly, violently, and, this is the key, predictably. It's like the universe built the perfect machine just for making these waves.
And this perfect little cosmic machine gave scientists a golden opportunity. Now, remember, at the time, actually detecting the waves directly was pure science fiction. The tech just wasn't there. But what if they could see the effect the waves were having on the system that was making them?
Think about it. Einstein's theory made a really clear, testable prediction. If this binary system is constantly blasting out energy in the form of gravitational waves, that energy has to come from somewhere, right? It's not free. And the only place it can come from is the orbit. So as they lose energy, the two stars should be getting closer and closer, spiraling inwards.
But just stop and think about the sheer insanity of that challenge. These stars are thousands of light years away. The change in their orbit would be tiny, absolutely minuscule. We're talking about a change so small it's almost unimaginable. Was it even possible for astronomers to measure something that precisely?
The answer, unbelievably, was yes. And what you are looking at right now is no exaggeration one of the most important graphs in the history of science. Let me be clear about this. That solid line isn't some best fit curve drawn after the fact. That line is the prediction from Einstein's equations, and the dots, those are the real-world measurements taken over years and years from a pulsar system called PSR B1913+16. I mean, look at it. The match is just perfect. It's stunning.
It wasn't just close, it was a 99.7% match. More than 99.7%. This was it. This was the smoking gun.
The official conclusion, as you can see, was clear. The effects of gravitational radiation have thus been detected. This wasn't just some academic exercise that proved an equation was right. This was the first real, concrete evidence that gravitational waves were not just a theory. They were real. And yeah, you better believe it won a Nobel Prize.
But the story was far from over. This pulsar proved the waves were real by showing us their shadow, their effect. The next great challenge was to actually catch one of the waves themselves as it passed by Earth. And scientists knew there were even bigger fish to fry out there. They were dreaming of things like colliding black holes, events so violent they'd unleash more energy in a split second than every single star in the universe combined. Just think about that.
So, there you have it. Einstein drew up the map. A couple of tiny, distant pulsars proved the destination was real. And now, today, we've finally built the ships to travel there, detectors that can actually hear these cosmic whispers. Which leaves us with the most exciting question of all. Now that this new window to the universe is finally open, what are we going to find?